I'm going to be talking about the transient heat characterization of sword cross-sections during quenching. Japanese sword making has been around for centuries, in which high and low carbon mahogany steel is used for the sword. When the final shape is obtained during the forging process, it is heated in a furnace and then quenched. The geometry of the cross-section is diamond-shaped with heights h1, h2, and h3, and width w. The convection coefficients, little h1 and little h2, are determined based on the desired clay thickness and surface temperature. The FEM study involves using 228 constant strain triangles with 128 nodes to model the cross-section. The convection coefficients for the gamma-3 boundary condition are determined based on the desired clay thicknesses and the average temperature of the starting and final surface temperature. Steel is used for the cross-sectional material. Time integration is done using Crank-Nicholson by heating the sword to 750 degrees Celsius, plunging it in a bath of 25 degrees Celsius water, letting it cool to its final steady-state condition. The cases studied involved varying the height dimensions, the width dimensions, as well as the convection coefficient. And so as you can see, as the height dimensions change, there isn't a very significant difference in terms of the temperature distribution or the cooling rate. Whereas when the sword is made thinner, there's a significant change in the cooling rate as well as the temperature distribution across the cross-section. And so what this means is that the thinner sword is going to have a lower quenching time. Now let's suppose the swordsmith had an off day and made the convection coefficient due to the clay thickness asymmetric, which we'll designate as little h3. What you can see is a temperature distribution that is asymmetric, but it has a relatively similar cooling rate as with the proper distribution of clay on the edge. And so as the sword cools, the one with the proper clay thickness has a bit faster cooling rate, but it's still within the same cooling rate as the asymmetric case. And so we used the FEM model to model the quenching process of a Japanese sword by varying the cross-sectional dimensions and the convection coefficient, and showed that the thinner cross-section requires much less quenching time, while the asymmetric convection coefficient on the edge induces roughly the same cooling rate but an asymmetric temperature distribution. Thank you.